This is Mrs. O'Neill for AP Chemistry, Chapter 17, Section 1, Additional Aspects of Aqueous Equilibrium. So you should look at page 739 and look over those key terms. Make sure you understand them. Water, the most common and most important solvent on Earth, occupies its position of importance because of its abundance. Remember, a lot of, and its exceptional ability to dissolve a wide variety of substances, aka is the universal solvent. Coral reefs are a striking example of aqueous chemistry at work in nature. Coral reefs are built by tiny animals called stony corals, which secrete a hard calcium carbonate exoskeleton. Over time, the stony corals build up large networks of calcium carbonate upon which a reef is built. The size of such structures can be immense. So in this section, we're going to learn about the common ion effect, and the objective is to understand a specific example of Le Chatelier's principle known as the common ion effect. So first, few questions. First of all, what does common ion mean to you? What is a common ion? Now let's think chemistry. It's an ion that will exist in two reactions. It's an ion that is common between those two. So the two reactions are happening at the same time. One of those reactions is going to be a strong reaction, and one of those reactions is going to be a weak reaction. So these strong reactions are very similar to what you saw in Chem 1, and these weak reactions are going to be what you saw in the equilibrium chapters 15 and 16 that we just did. So how does one of those reactions affect the other? Well, you're going to use this Le Chatelier's principle to see what the disturbance does. So let's remind each other what can be strong. Your strong acids on the list, your strong bases on the list, and your ionic compounds. They're also called salts. So an ionic compound is also known as a salt. But all of these are strong because they break into ions completely. So what happens when NaC2H3O2 is added to a solution of HC2H3O2? Well, this ion, this acetate ion, is going to be your weak base. Therefore, what's going to happen to the pH? Well, that's going to increase, meaning that our H plus concentration is going to decrease. Well, why? What happens? What's going on here? Well, like I said, there are two reactions to look at. First, we need to figure out which of those substances is going to be a strong reaction and which one is going to be weak. Again, the reminder, strong goes to completion where weak is in equilibrium. So we're going to use that Le Chatelier's principle to see what that disturbance does. So here's our principle. So first thing is first, salt is going to be that strong electrolyte. How do I know? Well, look at that arrow, right? It goes to completion. So this is an ionic compound, sodium acetate. It's going to go to completion and break apart into its two ions. Then we have the weak guy. Well, we have acetic acid, and that acetic acid is weak, breaking up again into H plus and that acetate ion, but again, this one's going to be in equilibrium. So what ion is common in both of those reactions? Aha! So when we add the strong stuff, right? So when we add this salt, it's going to break apart into ions. That ion now has more of this stuff. Did you not learn last chapter that if you add something, it's going to shift to get rid of it? Aha! So when we're adding that common ion, it's going to shift this equilibrium reaction, the weak guy, to the left to make more of our weak acetate, to force these two to react with each other and make more of that weak acid. So again, it's going to shift to the left, and we have all of this information that I just said. So if you haven't done it already, pause the video and fill in the notes. They look a little different this time, but everything is there. So common ion effect, again, pause. Read as you write, guys. Just don't fill in those words. Read as you write, because everything that I just said is basically said here in just another form. So hopefully this makes sense. So why do we need to learn this? Because we got to do the problems. Of course, everything comes down to problems. So Example 1, let's do this one together. So we're going to answer some questions first and then look at this. Because we're dealing with one of those reactions being in equilibrium, we're going to use that icebox. So my first question is, which is strong and which is weak? We have two substances we're dealing with, HCl and HF. In this case, they're both acids. Well, one better be strong and one better be weak. So hopefully you figured out that HCl is your strong guy and HF is your weak guy. If you didn't, notice this. They give you a Ka for HF. So that must be your weak guy and the other guy must be strong. So there you go, strong versus weak. Got that? So these are going to be everything that's in our pot, okay? That's going to be everything that's in our solution when we mix these two together. So these are the two reactions we're dealing with. We're dealing with a strong reaction and we're dealing with a weak reaction. So does this make sense? HCl is not going to be one of our species in solution. H will be, H plus, Cl negative will be, HF will be, and of course there's your common ion, and of course F negative 1. So the only thing that's not in our solution is going to be that strong guy, which should make sense. It completely dissociates into ions. Oh, I already answered this question. What is the common ion? That H plus, okay? But we are asked about in our problem about that fluoride ion. So we're actually asked about the fluoride concentration. So really that's the equation we are interested in. So I answered some questions, and now let's fill in that icebox, okay? Oh, and before we move on, we want to remember that the concentration of our acid is really going to equal the concentration of the H plus, right? If we had 1 molar HCl, we have 1 molar H plus and 1 molar Cl minus. On the other hand, with the weak guy, we really don't know that, right? If we start out with 1 molar of HF, we don't really know. We need that equilibrium molarity, those equilibrium concentrations, and that's where that icebox comes in. So this is our icebox. One thing I want you to notice is it's still ice. Instead of putting reaction here, we have two reactions. We got the strong reaction and the weak reaction. And notice I put the common ion, hint, 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 together. We also want to remember that this icebox really is only for the weak guy. So what substance is the common ion? I already answered that, so I'm going to put common ion there just as a reminder. Now my next question is, remember for the strong, the concentration of the acid equals the concentration of the H plus. So we can actually put that information right there. So hopefully that makes sense. This 0.1 molar HCl really comes from the 0.1 HCl here decomposing, right, separating into ions to that 0.1. That's where that value goes. Where the HF, right, it gives us the 0.2. That's going to be our initial. So how much of this guy, of the F minus, do we have? 0, right? So what's the next thing? Do we know any of those concentrations at equilibrium? They don't give us any other information. So now we're going to use that X. We did that last chapter. So now we can fill in our change as positive, again, negative here, positive for the reactants, and now we can solve for our Ka. Okay, now when we solve, or I should say use the Ka to find our X, we're trying to find that, that's actually our F negative, right? So think about what we need though for pH. To find our pH, we're going to need this H plus concentration. And when we solve for X, we're really only getting F minus. So can we plug and chug, right? Our Ka they give us. Now we're going to use the formula this way. We're going to plug in our X's. But let me remind you, what can we do with those X's? We can get rid of the plus X and the minus X. Now we got to leave this guy. We got to leave that guy in the equation, but the plus X and the negative X we can get rid of because, again, we're going to assume less than that 5%. So then we kind of plug and chug, excuse me, and we get X equals 1.4 times 10 to the negative 3. Again, molarity because we solved for concentration, but that's not what we wanted, right? Because of that, we want to find pH. The only way we can find pH is to solve or to have the concentration of our H plus. So 0.1 plus X, right? That 0.1 plus X to give us that H value. And we kind of plug and chug along, and hopefully you know to take the negative log of that guy and get the pH of 0.99 or 1.00. So hopefully that makes sense, but we do have more examples coming up. So same thing, we're going to need to make the icebox. We need to know what is strong and what is weak. And in our icebox, we should have two equations. We should know what is the common ion. So can you fill in the icebox at this time? Pause the video and see if you can fill that in. Hopefully you got your strong guy and your weak guy. And as a reminder, this icebox is only for the weak guy. Then what's our common ion? That H plus. Ooh, if it's asking for pH and our common ion is the H plus, well, if that's going to be our X at the end, woohoo, maybe we can skip a few steps. So can you fill in the initial concentrations from the information they give you? And again, the CHO negative, CH2 negative is 0 initial. Our change is going to be that X again. Can you plug and chug? Again, pause the video and can you solve for X? This is not as easy as I thought it would be, right? We have our H plus, even though it's the common ion, we are solving here for that CHO2. So can you reformulate that algebraic expression? Again, as a reminder, we're taking away the plus X and the minus X, but we're leaving that guy. And again, we're plugging and chugging away. So very similar to what you just did. Excuse me again. So we have the pH of 1.00. Okay, example 3. Uh-oh. Now they're giving us moles, but since they're giving us 1 liter, really our moles equals molarity, which is very, very nice. So again, pause the video. Can you make the icebox? Your strong reaction, your weak reaction, and then can you fill in any other parts? So hopefully you got this. You got your strong guy, you got your weak guy, your icebox is only for the weak reaction, and you got your common ion here. So can you fill in the moles? And in this case, since it's per 1 liter, like I said before, it is molarity. Now we have our X's. So our X though, oh, here it is. Our X equals our H plus. That's really nice. So we don't need to do that extra step. So can you pause? Can you plug and chug and find the X value and then solve for pH? Hopefully you got that, that, and that. And again, if you have H plus here is just as good as H3O plus, just as good. It doesn't really matter which way, but I wanted to show you that you're going to see both ways. And over here, again, I did get rid of the minus X and plus X right away. So example 4, give it a shot. Again, which one's strong? Which one's weak? Fill in your icebox, fill in as much information. If you don't have the change, it's going to be an X. Rearrange, solve for X. Does that X give you the common ion or does that X give you the H plus? And go from there. So here's our icebox. Hopefully you can fill all of that information out. Hopefully you can figure out the K and solve for X. And in this case, again, your X value is your H plus value. So then you can plug and chug for pH. So give it some thought, pause, and see if you can come up with some answers. Hopefully that you got. And that you got. This, ladies and gentlemen, is going to be a really, really important reaction. I brought this to your attention way back in the day in the beginning of the course, and it's going to be even more important come this chapter. Okay, see you in class.